There we go. Okay, there. So the show has officially started. Welcome back. Welcome back to the basement where I am only temporarily. I've already been let out of today earlier, so. We have, let's see, lecture 3 to do today, example 3 to go with it. That'll still take us the next several classes or so because level 1 predictors are a complex topic. You have a homework out that you should be working on that is due Wednesday, not Monday, since we spent an extra day on example 2. I had already asked for questions about that, but if you get stuck on things, please let me know. And if you get yourself unstuck in the period of time it takes me to respond to your email, let me know that as well, because then that's one less thing that I have to do. So thank you for those updates. Let's see here. Everybody can hear me and see me? I take it? Okay, same rules apply. If the microphone cuts out or my video lags or whatever, please let me know immediately. I did not intend to mess with the mic or the video or any of that stuff. So, making it work, continuing to be the theme into 2023. All right, so away we go then. New topic, but first, a review of the old topic. So this is week 3 of the semester. We've already gotten involved in the wonderful world of multi-level models for clustered data with respect to empty models and adding level 2 predictors. So the big picture, the idea of multi-level models, they are designed for analyses in which your outcome variable is collected across more than one dimension of sampling. So in the longitudinal class that I taught last year, we had repeated measurements within the same person as and different people as the 2 dimensions. This year, it's going to be differences across people and differences from across the clusters from which they were taken. So level 2 is cluster as the macro, level 1 is micro. Want to see the transcript? Yes, let me find it. Thank you for the reminder. Where'd it go? I'm looking at all my apps here. Where is the transcript button? Hang on. Okay. Is the transcript on? Is it working now? For those of you who watch that? Okay, good. Yeah, I never watch it because it just throws me off, and then it has funny things like, you know, a Rambo instead of Remel, or fish sticks for fit statistics. That's my personal favorite. So if I pay attention to the transcript, then it's all over, but glad we have it. Okay, so level 2, macro, between. Level 1, micro, within. Those terms always work regardless of what type of sampling design you have, but in the context of clustered data, we would say level 2 is between clusters, so far just referring to mean differences via random intercepts. And level 1 is within clusters, the E variability, person-to-person differences that remain after controlling for which cluster you're from. So we would have something like this here on slide 2, an empty model for P is for person, C is for cluster. Beta 0 is my placeholder for how each cluster gets their own intercept, which is defined by a fixed intercept in red here. That's the mean of the cluster means, plus the U, which is the random intercept for each cluster, which has a mean of 0 because its mean is the fixed intercept. So fixed plus random together make a whole variable. Fixed is always the middle. That means that fixed always comes before random. Once you give each cluster its own mean, then E fills in what's left to get to each individual person's outcome. So E is the difference between your outcome and the cluster mean. So all in all, 3 parameters would be estimated for a model like this: the variance across clusters in the U's, the variance across people and clusters in the E's, and then the fixed intercept. Terms of describing how much variability we have at each level, very important descriptive statistic interclass correlation for that. ICC1, as it is known more formally, gives you the proportion of variance that is between clusters due to mean differences, or the expected correlation of people from the same cluster. Either way, you can talk about that number. And if we put in level 2 predictors, which is what we've done so far and what you get to practice in homework 1, those are cluster characteristics, so they are constant over people from the same cluster, which means that cluster characteristics can only explain level 2 random intercept variance. So in terms of an R-square for effect size, we would focus on level 2 variance specifically. If we want to put it back all together again, that would be total R-square as an alternative complementary effect size. Okay, good so far? Any of that you want to ask me about before we jump into something new? Okay, then here it is. This is my public service announcement. If you remember nothing else, remember this: no smushing allowed. That is the number one thing people mess up in multi-level models. So the first slide here is setting up the problem, what not to do. So if level 2 predictors, which I've given an example here, level 2x with a C, varying over clusters only, are cluster characteristics, that means level 1 predictors are people characteristics. So level 1x gets a PC because it varies per person per cluster. So what if we just put a level 1 predictor in the model, straight up, just like we did a level 2 predictor? So we might center it. So C1 would be a constant up to U. That would make the scale of the predictor include a meaningful 0 point. We might put in our level 2 predictor and center that at a constant that would make its 0 meaningful as well. Throw it in the model. Then beta 1 would be the new placeholder for that level 1 slope. So at this point, clusters have two different placeholders. The intercept stays in. Beta 1 is a slope for each cluster that is defined by just this one term here, a fixed slope. So each cluster would have the same expected coefficient for what the relationship is between this level 1x and this level 1y. And because we're referring to beta 1 as the new outcome at level 2, this fixed slope starts at 1 because it goes with beta 1, and it's the jumping off point for how beta 1 forms its slope. So 0 in the first, and if we added other predictors here, then they would start with a 1 as well. So, looks reasonable on the surface of it. And I will tell you that I inspected a couple newer textbooks that have been written on clustered multi-level models for this class, and they screwed this up. So the second I saw that, I was like, nope, close the file. This looks like it could be reasonable, but it's not. The reason is, for the same reason that we have to pay attention to the fact that Y has at least two different kinds of variance in it, cluster differences and people differences, X does too. So level 1x, what you're thinking of as one column in your data set that varies over people, almost always is going to vary over clusters too. And that means putting in one slope for it is going to have to do the work of two different slopes at a minimum. And unless those two different slopes are exactly the same, this model is wrong. Empirically, testably, defendably wrong. So, the classic example that is used to introduce this problem in the older textbooks, including the Snyders and Bosker book that I've stuck with here, is socioeconomic status, of students who attend the same school, abbreviated SES. So it is likely the case that in any given school, some kids are from families that have more resources. So within a school, some kids may have higher SES than other kids from that same school. We can represent that idea by taking the difference between the school's mean for SES and each individual's score. So how much richer are you than your peers would be the within part of that variable that is level 1 person to person within cluster differences. At the same time though, children are not randomly assigned to schools, particularly in the US where what public school you go to is tied to what neighborhood you live in, and neighborhoods have different values of homes, and sales of home and the taxes on home are what partially support public schools. So resources are not randomly assigned. Students are not randomly assigned to schools. Some schools are going to have students who have more resources, and therefore the school indirectly is going to have more resources. So to the extent that some schools have richer kids than other schools, even though I'm thinking of this as a person characteristic, SES is also a school characteristic. And so I can take the average across students from a school, we call that the cluster mean, and that forms a new variable in my data set, and I can use that as an index of between cluster variation in this level 1 predictor. The extent to which I need to worry about this, you can find out by taking your predictor and estimating the same empty means random intercept model that we would for an outcome. So interclass correlation varies between 0 and 1, right? If I have an intraclass correlation of 0, what does that mean?
No level 2 variance.
No level 2 variance. An intraclass correlation of 0 means no dependency, no cluster mean differences, no level 2 variance. If I have an ICC of 0, there's no cluster differences, yes. That means there can't possibly be a relationship between my predictor and an outcome at level 2. If my predictor doesn't have any level 2 information in it, then there's no way that it can relate to that of an outcome. So if I have an ICC of 0, my predictor is purely level 1 within. Well, what if I have an ICC of 1 instead, the opposite?
No within differences.
Yep, no within differences. Then what I thought was a people thing is actually just a cluster thing. So if that were the case, what I'd actually have is a level 2 predictor. So that's another way of thinking about the level 2 predictors that we just covered, is that they are variables with an intraclass correlation of 1 because they are constant over the level 1 units from that cluster. So if I have an intraclass correlation of 1 for a predictor, it's only a level 2 predictor. That means there's no way that it can have a level 1 slope because it doesn't have any level 1 information in it to relate to the level 1 information in an outcome. So those are the extreme cases, but almost always for observational data where you're not manipulating something, you're going to have a predictor that has some of both, an intraclass correlation somewhere between 0 and 1. So to the extent that a level 1 person predictor has person variation in it like we're expecting, it can have a level 1 within cluster effect, the effect of being more than your peers at something on your own outcome. To the extent that your level 1 predictor has some level 2 information in it, that clusters differ in their means on this level 1 person variable, then you have the potential for a level 2 between cluster effect in addition that is separate. So they are two logically separate things, likely buried within one variable, and that's the problem. So how would that relate then? So if I carry the SES example a little bit further and talk about student achievement, it may be the case that within clusters, kids that have more money than other kids, that have higher SES than other kids, may have relatively greater achievement than other kids as well for their outcome. So within schools, kids that have relatively more resources may have relatively better outcomes. But it's also the case that schools that have more resources, right? Schools that are populated with children who have resources may have better outcomes at the school level than schools who are populated with children with fewer resources. So both of those things can be true at the same time. In both cases, the more resources you have, the more achievement you have, the slopes would at least be in the same direction. That's not necessarily going to be true though. Here's another example that I stole from Curran and Bauer from their chapter. It was from, not a chapter, it was the Annual Review of Psychology in 2011. And Patrick heard a story about this on NPR one morning, and that's how it ended up in this writing. So I heard about that on their podcast. So within animals, there is a different relationship between body mass and life expectancy depending on what your level of analysis is. So within a species, like if you narrow down to just one kind of animal, like ducks, if you have a relatively bigger duck, he's likely to have a lower life expectancy than a smaller duck. So overweight animals have a worse life expectancy than regular weight animals. But if you go across species, the opposite is true. Larger species tend to have longer life expectancies than smaller species. So whales live longer than cows, who live longer than ducks. So if you were to talk about what is the relationship between body mass and life expectancy in the animal kingdom, right? These are two different answers to that question, and they both make sense because they're talking about relatively different sources of comparison within a species or across different species. And in this case, one slope would be negative while the other would be positive. Now that might be an extreme example, but it is possible in regular research settings and studies with people that you could see slopes in opposite directions like this at the same time. So that's one reason why you would expect the level 1 within slope to be different from the level 2 between slope is both conceptually what it represents, but a simpler reason is just math. All of these slopes are unstandardized. They are scaled in terms of units of x versus units of y. And you have to know what the units of each are to know what the slope means. There's no such thing as standardized slopes in multi-level modeling. No one has agreed on how to do that. because standardization refers to the variance of x and the variance of y, and that's going to be level specific. So the only situation in which you could have slopes that are the same would be if the variances going into them are the same, meaning that you would have the same amount of variability at level 1 as you do at level 2 in x, and the same would have to be true in y, and then the relationship would have to be the same across levels. So all of that amounts to not very likely that you would see these two types of relationships be the same number, even if conceptually it would make sense that they at least go in the same direction. Okay, how are we doing so far? So big picture, first thing we did with y is figure out how much of its variance was between versus within. Now we're going to do the exact same damn thing on the x side. How much is between versus how much is within. And the between parts can be related, the within parts can be related. That's the big picture. How to set that up is the smaller picture that will take us a while to get through. So the terminology then, I only need one headphone. I feel weird when I have both of them in here. Comment from the chat window, the more classes I take, the more it seems that no research has ever been done correctly. Yes. The way that I would look at it is that across our research careers, myself included, our job is to try to do the least wrong thing that we know how to do. Right is an illusion. Least wrong is all you can reasonably hope for. And yes, if you look at the literature, you will see sort of tendencies of things to shift and how people do things as more information becomes available in terms of what the best way to do it is now, as opposed to what the best way was 10 years ago, but also the software and the estimation capabilities to do what is relatively best. So I have papers like from when I was in grad school that are just straight up wrong. Like if I knew now, like if I knew then what I knew now, I wouldn't have done it that way. But it was the best I knew how to do in 2004. That's the reality. So we're always striving for least wrong. I can tell you that this model right here on slide 6 is the most wrong thing you can do in the world of multi-level. It is the most wrongest by far. So I call this coefficient right here the smushed effect. The idea that that phrase came up with is because whenever I talk about this, I make this gesture of like level 2 up here and level 1 up here. And when you force both slopes together, it's like you're smushing them into each other and it's just one thing. So this is where smushed effect came from. See, the people on YouTube don't get the visuals with this. This is the extra tuition dollars at work here. You get to see this. Now that's my word. And it is slowly creeping into the literature. There are a few papers that use it that I didn't write. And of course I use it in every paper I write because my papers sound like I'm talking. I don't know how to do it any other way. But if smushed effect makes you feel a little bit too informal, my second place term that I like is conflated. I'd say that one is probably the most common because it's conflating two different things. Convergence would be next on my list because you're assuming convergence of the within slope onto the between slopes. I have a visual that goes with that here several slides later. Another one I've seen is composite effect, but I don't like that one because that's a little more ambiguous as to what a composite is of. So I like smushed effect, but conflated would be my second choice. The key idea here is that level 1x has both a P level 1 part and a C level 2 part, but you're only giving it one slope. That one slope has to do the job of two different things. That's the problem. This problem, by the way, is also familiar to others from other disciplines such as economics and some other related social sciences. I think to some extent political science has this too, as the problem of endogeneity. So in those fields, there's often debates as to whether you should address your clustering using fixed effects or random effects, where fixed effects means you would treat your cluster variable as a predictor. Like you would put in cluster ID as a predictor that's categorical in your model, and you would have number of clusters minus 1 fixed slopes for those binary dummy codes that distinguish each possible cluster. If you do that, then you have solved or prevented the problem of smushing, because those fixed effects have soaked up all possible cluster differences on the outcome side. There's nothing left for your predictors to do on the X side. all level 2 variance has already been taken care of. So there are tests that you can use to decide whether or not you should have fixed effects or whether you can use random effects. And if the tests say that you need a fixed effects model, it's because of this problem. If you put in a fixed slope of a level 1 predictor, and that slope does not have the right level 2 component to it, then the residuals for your random intercepts are going to be related to your predictor, which is violating endogeneity. So I put a couple articles on your reading list about this problem in case any of you are from fields where fixed versus random effects is still a thing. You can refer to those papers, but know that we are talking about the same problem. These are just two different ways of addressing it. Switching to fixed effects is one, staying with random effects and setting up your model correctly is what I'm going to show you. Yes, statistics is boundless in scope. I would agree with that comment too. That's the curse of knowledge. The more you know, the more you realize how much you don't know because you realize how much is out there. So every day I feel just a little bit dumber than the day before. All right, we doing okay? Yeah? All right, am I talking too fast? No? Okay, good. That means I get to refill. You cut me off if I go too fast. So, graphically, I'm trying to use pictures to make this a little bit easier to digest than just equations and such. The problem looks like this. So on the y side over here, we have this observed variable. So I'm sort of borrowing SEM conventions where observed variables are in boxes and estimated quantities, latent variables or imaginary variables are in circles. The first thing we did when we get our multi-level outcome here, y, is figure out how much of its variability belongs at level 2, random intercept over clusters, versus E variance at level 1 within cluster differences, right? That's the first thing that we did. Well, over here on the x side, we're not doing that. If you just put in a slope of how x relates to y, what you're actually saying is that the level 2 embedded green part here, yes, colors on purpose, has the same relationship in predicting the level 2 intercept of y as it does in the level 1 part predicting the level 1 residual of y. So it's like you're saying these two paths conveying the regression slope are being constrained to be equal. So we don't want to do that. We want to be able to allow them to be separate. That's the end goal here. There is some literature figuring out the math for what you can anticipate your smushed effect to be. This is an equation that I adapted from the Radenbush and Bragg textbook. I have a reference to it there. And what it shows is that it is a blend of what the between cluster effect would be at level 2 plus the within cluster effect at level 1, but it's a weighted blend. So it's weighted by the standard error for each of these things squared, or what is otherwise known as the sampling variance of these slopes. And because the level 1 effect is going to have a much smaller standard error, it's based on a lot more people. Usually there's a lot more information at level 1. That means that the smushed effect is going to get pushed to look much closer to what the level 1 within slope would be than the level 2. So it's a smush, but it's uneven. It's going to be much more driven by level 1 in most cases. So when you fit a smushed slope, it's actually the level 2 model that is going to suffer in most cases. Level 1 is going to be reasonably close most of the time. And they have a quote in the Snyders and Bosker book that I like. It is the rule, not the exception, that these slopes differ from each other. And yes, that is usually what I find in example data sets, in student projects, and in research, that they should differ from each other for conceptual and mathematical reasons. So, and then a nod again to the issue of endogeneity here. So what are the slopes that we can have, and what do they mean? So there are 3 different kinds of slopes that we would potentially be concerned about for any level 1 predictor, and I'm only talking about a main effect for right now, meaning just X predicting Y, not interaction terms or anything crazy like that just yet. So a level 1 slope, if you put in a level 1 person predictor, this is the one that you probably had in mind when you added that predictor. So at level 1, if I have a higher predictor than other people in my cluster, so if I'm within cluster centered, essentially within clusters relative to my peers, If I have more X than they do I also have more Y than they do? That's a level 1 within slope. And if so, then that relationship should cause your level 1 residual variance, the within variance on the Y side, to be explained, to be reduced. Second one, also straightforward. It's the opposite, it's level 2. And I'm going to be using color deliberately throughout this slide deck. Purple is for level 1, this type of green is for level 2 between. Between cluster slope is if I take the aggregate across my rows from the same cluster. So I compute a cluster mean across rows. And I take that cluster mean and I merge it back into the data set. So I take the same cluster, gets the same mean throughout all their rows. That's a new level 2 variable. So then if I'm from a cluster that tends to have a higher cluster mean on this person variable than other clusters, then does my cluster have a higher outcome than other clusters? So it's an aggregate of the person information up to the cluster information is what we're talking about here. If so, then the cluster mean of the level 1 predictor, the cluster's average across people, that variable should then explain level 2 random intercept variance for mean differences across clusters. So we're taking the idea then behind these two, the easiest way to do it is to literally break the level 1 predictor into these two parts and fit a slope for each part that is level specific, and each one does its own job. The third one, I'm going to introduce it and I'm going to put a pin in it, is another type of level 2 slope, but it's contextual is the name of it. This one is tricky to explain. I'm going to try it from about 3 different perspectives. I picked up a new one. We'll see if this makes it better. The way that it is often explained is after controlling for the level 1 predictor's slope. What is the incremental effect of the cluster mean? That is the way, the motivation behind the term context, and that is commonly something people want to know in organizational research. After I control for individual characteristics, what is the extra influence of the group that I belong to in terms of their standing on average for this predictor? The between slope is also level 2, but it does not control for level 1. The contextual slope does. So that's the primary difference in terms of the interpretation between and contextual. An easier way to think about it in my book is to say that the contextual slope is the difference of the between minus the within. Empirically, whether or not a smushed effect is adequate, or whether those within and between slopes are sufficiently different that you really should keep them separate. My view is that they stay separate pretty much regardless. But if you ever needed to demonstrate that, I'll show you how it's through a contextual slope. So 3 new vocabulary terms here. Level 1 within slope, relatively better than your cluster on X. Does that translate into relatively better than your cluster on Y? Level 2 between. If my cluster is higher on X than other clusters, does that translate into a higher cluster mean on Y? And then level 2 contextual, which is if my cluster is higher than other clusters, does that still translate into a higher cluster mean on Y after controlling for the level 1 person value? Incrementally. That's the idea. Do I have pictures next? Do I have pictures? Yeah, I got menu then pictures. Okay. How are we doing? Yeah. I expect some sideways is like my best hope right now. Because this stuff gets very like, what? I've got examples, I've got pictures, I've got equations. I'm going to throw everything I can at this. But this is the beginning. And I will repeat it, and I will go as slow as we need to understand this, because this is essential. So here are 3 strategies we're going to talk about. 2 in detail right now. 1 is going to be introduced briefly and then put back into the story later in the semester, of how you can make sure that you are not smushing effects of level 1 predictors. How you can make sure that you have properly differentiated what is a level 1 within relationship from a level 2 between relationship. 2 of the strategies are within the framework of what I call univariate multi-level models. So univariate means you're predicting one column. That's what Elmer does. That's what SAS data and SPSS mix do. You're predicting one column at a time. So even though your data set is technically multivariate in the fact that you have repeated measures from the same cluster, like conceptually, like it's just, math or language, right? It's one variable and it's one column. So the first two strategies have to overcome the limitation that your model can only predict one thing at a time. It can't predict X, it can only predict Y. So the easiest thing to do, this is my preferred method for everything because it is the least likely to be screwed up, is to do what is known as cluster mean centering. There's 1,001 synonyms for this, by the way. It can be group mean centering, cluster mean centering, centering within contexts, in longitudinal variables, it's person mean centering or within subject centering. The general idea is that you are centering using a variable instead of a constant. That fundamentally alters the information that is contained in the result. So what we'll do is literally subtract off the level 2 part from the variable, save that as a new variable, and put that in the model separately. So cluster mean centering removes the level 2 mean variation from the level 1 predictor, leaving only the level 1 within information. Then the level 2 mean information goes in the model separately. The reason I like this is because no matter whether you have one variable or the other variable or both in at the same time, if you set up your variables like this ahead of time, you are guaranteed to know what you get back. A level 1 predictor can only yield a within slope, and a level 2 predictor can only yield a between slope, the and. That's why I like it. The second option is more complicated. You don't do the work on the front end in terms of building your variables to maintain level-specific interpretations. You do your work on the back end after statistical control does it for you. The second option is to not carve up your level 1 predictor, but to still control for the cluster mean as a separate variable. So this is where you would center using a constant rather than a variable. It goes by the name grand mean centering most commonly because the constant that's usually chosen is the grand mean, but it doesn't have to be. Anything, any constant, even leaving it uncentered so that 0 is 0, would accomplish the same thing. The critical thing is adding the level 2 mean in to keep it unsmushed. This, if you do it properly, will always yield level 1 within slopes and level 2 contextual slopes, but only if the two are together. If they're not together, then the interpretation changes, and we'll show that what happens with that. The third option is something that we'll wait till later in the semester to see examples of because it requires M+ software, multivariate software instead. So what is known as multi-level structural equation modeling, you can also use regular structural equation modeling to do this to some extent, although the data manipulation is tiresome. The idea is to just treat X like you would treat Y. Well, if I'm going to ask the model to figure out for Y how much is level 2 random intercept versus level 1 residual, why don't I do that for X at the same time? Easy peasy. Then I let the level 2 variables relate to each other however they want. The level 1 variables do the same, no problem. That is known as latent centering because you're centering using a latent mean instead of an observed mean, but 1 and 3 are directly analogous to each other. The difference is whether you're using latent variables or observed variables in your analysis. If it's latent, it has to be multivariate. The tricky part then is figuring out exactly what you get back at level 2 because that varies as a function of type of model, type of syntax, and type of estimator, at least within M+. And I sat down and tried to figure this out, and it made me so frustrated that I pounded out a paper about it, and there it is. So I figured no one else is going to have to go through the pain that I went through in having to figure this out, and I'm going to write it down not only for myself, but for other people as well. Question, so does cluster mean center level 1 with its grand mean and level 2 with its respective grand mean? If I understood the question, let me answer it with the next slide. It's like I knew it was coming. Level 2 is centered at a constant. You are welcome. Level 2 is centered at a constant. So what's going in when we're doing cluster mean centering is the way to read this notation is it's the mean of level 1 X, that's why the bar is over that, and it varies only across clusters at that point. So there's no more people information, it's all just cluster means. I'm centering the cluster mean at some constant so that 0 is within the scale of my cluster mean variable. And I'm calling the result of that CMX for cluster mean X. What C2 is entirely up to you. It honestly doesn't matter. What it matters for is interpreting the fixed intercept, because the fixed intercept is always when your predictors are 0. That rule hasn't changed. It also matters if your cluster mean variable is going to become part of an interaction term, because then the simple slope of its other interacting variable is specific to its 0 value as well. So having 0 be meaningful makes things more convenient. It doesn't necessarily hurt anything if it's not, but that's just good practice, I feel like, good housekeeping. So cluster mean X goes in at level 2, centered at a constant. Its job is to predict random intercept variance because it is a level 2 predictor. Level 1 then is the cluster mean centered part. So we take my original level 1 X that varies over people and clusters, and we subtract off that new variable that we made for level 2. So this is not a constant, this is a variable. This is a new column in your data set that has the mean for that set of rows, and then you take your original variable minus the cluster mean, and the result, which I'm calling within cluster X, then what 0 means on that new variable is that you are at your cluster's mean. Like you are an average student with respect to your cluster for that predictor. A positive value would mean you're above average for your school, your cluster. Negative would mean you're below average. And that's a little bit weird to think about just being relatively high or low relative to your cluster. But it's okay because where your cluster is in an absolute sense goes in at level 2 where it belongs. So the end result of this process is that we've taken our original variable, level 1 X PC here, and we've carved it up into 2 piles. We have level 1, which is just person-to-person variation from the same cluster, and then level 2 is cluster-to-cluster variation on average. Each one goes in the model, has its own job to do at its own level. So we've isolated the variance so that purple is only level 1 and green is only level 2. Okay, did that answer the question?
Yes, it did. Thank you.
Excellent, thank you. Other questions? Not yet? You reserve the right to change your mind. So here's what a model would look like. Sort of a generic model to start with, and I'll show you some numbers in just a sec. So at level 1, I would put in my new within cluster X, and here's a reminder as to what it has in it. So the original variable minus the cluster mean only has within information. That means that the slope that goes with this new cluster, so let's follow the notation here, beta 1c is how each cluster is going to get its own slope of this X variable. Peer-to-peer differences on X is what this is representing. Beta 1c then is an outcome in the level 2 model, but it's only defined by this one symbol here. Gamma 1o is a fixed slope, meaning this model is saying there's only one slope for the effect of within cluster differences in X, and that's it. All clusters share that slope. That's an assumption that we can test, but not yet. So 1o here, the fixed slope, is the effect of having more X than other people in your cluster. For every unit more X you have than the rest of your cluster, Y goes up by that much. Your Y, specifically that person's Y. At level 2 then, the green part. Cluster mean X is the cluster mean minus a constant, whatever constant, doesn't matter. And so then that goes into the level 2 model and it gets its own slope. So its slope is labeled gamma O1 because it's predicting beta 0, the intercept, and it is the first predictor of beta 0 as the intercept. So cluster mean X then is the effect of having more X than other clusters. For every unit more cluster mean X you have, your whole cluster's Y outcome goes up by that much. So purple is people things, green is cluster things. And because we carved up the variables into just the information per level ahead of time, we know that that's what their slope has to refer to. It has to be only within at level 1, has to be only between at level 2. Picture time. So diagrammatically, I should say, not grammatically. Most of what I say is not grammatical, let's be real. We have a symmetry here in how x and y are being treated, where y is being model partitioned into different piles of variance, level 2 random intercept versus level 1 residual. We're kind of doing the same thing on the x side, but with observed variables. So taking the mean across people from the same cluster and forming a cluster mean as a new variable, that is conceptually the same idea as having an intercept for x at level 2. And then seeing how far off you are on relative to your cluster mean on x is the exact same concept as being deviated from your random intercept on y. So this within cluster deviation box is directly analogous to the level 1 residual box. And the difference, these are in boxes because these are observed variables. The circles are the idea of model estimated variance components or latent variables that have model estimated variance. And if you're like, wait, why do these have to be boxes? Can everything be a circle? Yes, it can, but not yet. That's the idea of latent centering within multivariate, multi-level models instead. Okay, more pictures. All right, still with me? Maybe? Sideways? Sideways. 1 up, 2 sideways. Take it. Sideways is what I'm aiming for here. It's important to be realistic. How about some pictures? Let's say that I have X is student reading and Y is student math. Being able to read helps you solve math problems that have words in them. It's also the case that students who are good in one subject may be good in other subjects. So lots of reasons why reading and math could be related at a student level here. So if we keep the context of students in schools as our clustering. So let's say that I have data here on students. So I have 5 students from 3 different clusters. And the red cluster here has a school mean reading score of 4. The green one has a mean of 5 and the blue one has a mean of 6. So the connected dots here are students from the same school. What this plot is showing is an example of when you would have entirely a level 2 between slope, but no level 1 within slope. So the yellow line here depicts the slope that goes through these cluster means, the means for each school in this context, and the value that this slope corresponds to is 1. So for every unit higher mean reading, mean math goes up by 1. So that means that schools who have better readers have better mathematicians. That's what this means on whatever, fake scale I made up here. The fact that each of these individual lines here for each individual school is flat is illustrating a lack of within cluster effect. Within a cluster, kids who are relatively stronger in reading do not have any difference in their math. The slope is 0. So this would be only a level 2 effect, not a level 1 effect. The opposite would be the next slide. Wait for it. Flip back. Camera 1, camera 2, camera 1, camera 2. Camera 2 has all within, no between. So in this case, it's that students who are relatively stronger in reading, so if you're stronger than your school average, your math is higher by 1. But between schools that have higher reading on average do not have higher math on average. The yellow line has a flat slope of 0. The individual school lines have a slope of 1 instead. Here's some code to show you the example that goes with, get some numbers on here. This is from the same example that we started in the slides from my APA workshop, where we're predicting verbal ability in schools and students from the Snyders and Bosker textbook. And I have 2 level 2 predictors in the model still from before, how much homework they gave on average centered at 2, whether or not the school uses mixed grades. And to that we have added 2 new predictors. So the new parts to the equation relative to what we had in lecture 2 are highlighted in yellow. Beta 1 here, which is the within cluster effective verbal ability as a new student predictor. So note the notation, verbal PC, that's my original student variable in terms of their verbal ability, which is predicting their language test outcome. Subtracting from it a variable, not a constant. So this is illustrating cluster mean centering. What I'm subtracting from it is a column that contains the cluster means across all rows from the same cluster. So it varies over clusters only, which is why it gets a C here. So it's the mean of the verbal ability scores from students from that school. I'm giving it only a fixed slope for now because this is hard enough as it is, but that's the next unit, is adding on to this equation that looks awfully lonely right here. Right now it's just fixed, meaning that all schools get the same slope for how verbal ability predicts language outcomes. At level 2, I've also added that same variable, so verbal with a bar over it, C, that's cluster mean verbal, and I've subtracted 10 because in the scale of this, 10 was near the mean. So I can say that the reference point then for the model is a school with verbal scores from their students with an average of 10 for a student who is average for their school. So that's what 0 means between the two. It's like an average school and then for an average student with respect to their verbal scores relative to their school. Okay, does the setup make sense so far in terms of the variables? Okay, and yes, when you're writing papers and describing your models, writing out an equation can help people follow what you're doing if you do it correctly. I will tell you that I have lovingly created pages of equations and only to have the editor be like, yeah, take that out. No one's going to read that. So a compromise, if someone wants to kick your equations out of the paper, would be maybe an online supplement or an appendix or something like that, so that if anybody's interested, they can get the technical description. Otherwise, you can try to use words to describe it. But this type of showing the centering in the equation will help your reader track what 0 means. It's like if I see this, it's like, oh, okay, so this means they've done cluster mean centering. That means that a 0 value is someone who's average for their cluster with respect to this predictor. Oh, this is a cluster mean of that, so I know that that's not a separate level 2 variable. It was created by aggregating over these level 1 units, and 0 means that they have a score of 10. So down here in the output, this is SAS output, but I'll of course show you Stata in R. The 2 new variables then, CM verbal 10 corresponds to this one right here. So that means cluster mean verbal centered at 10. That's how I name my things. And then within cluster verbal is this one right here. So it's referring to the fact that it only has within cluster information after doing the cluster mean centering. So the intercept then, 41, that is the expected language outcome for schools that give a homework around 2, that do not use mixed grades, that have an average of 10 for their students with respect to this verbal measure, and for an average student. So only the last predictor here conditions the intercept with respect to a particular level 1 unit. The rest all just talk about level 2. But from here, both of these slopes are positive and both of them are significant. And this is where it gets tricky to keep your audience with you. Because you can't just say, well, this is the slope of verbal. Which one? The positive slope of verbal. Which one? What's the difference? The difference is in what it's relative to. The first one, nope, come back. There we go. The 3.6, that's a level 2 slope. Because I'm using cluster mean centering, I know that that is a level 2 between slope. So the way that I would interpret it is for every unit more cluster mean verbal, for every unit more average verbal across the students. Why? For the whole school, goes up by 3.66. The whole school. This is a level 2 effect. To the extent that this is significant, you should see the variability reduced at its corresponding level. So here's the variance components from the result of this model on the top. Here's the empty model for comparison. So our random intercept variance was 17. It's down all the way to 8 after the inclusion of these level 2 predictors. So to the extent that I go to a school that has stronger students on the whole, for every unit higher mean verbal, my whole school's language scores are predicted to increase by 3.6, significantly so. Then within. Within is relative to your school. So a within value of 0 means your average for your school, whatever that is. Whatever that is already in the model. So from there, I know what my school's prediction is based on my school characteristics. Now I'm getting to mine. For every unit more verbal I have than my school's mean, whatever that is. So for every unit smarter I am than my peers, my outcome goes up by 2.4. Mine, not the rest of the schools, just me. Within verbal is a level 1 slope or a level 2 slope? Let's make this a finger question. Within is 1, right? So which of my two variance components should it have reduced? 1 or 2? Level 1 or level 2, I should say. 1. They gotta match. If it's a level 1 predictor, it should account for level 1 variance. That's residual, that's the 40. So it was 62, it went down to 40. If it's a level 2 predictor, it should account for random intercept variance instead. More generally, you can look at the equation and anticipate which pseudo R-square you should be looking for. Any predictor whose fixed effect is listed in this beta 0 line is targeting U0. That's its job. That's what it's there to reduce. Any predictor that is in the level 1 equation is targeting E. That's its job. And gamma 1O here, once you do the substitution back into the placeholder, is targeting E. So within cluster verbal reduces level 1 residual variance, explains why some kids have higher language outcomes because some kids have relatively higher verbal ability. Level 2 cluster mean verbal explains random intercept variance. It says that some schools who have students with higher verbal on average are schools that have higher language outcomes on average too. So to try to recap, the tricky part here is making sure that you can clearly convey what each slope represents, but it boils down to more than what? More than other schools or more than other kids in my school. If you keep those two reference points in your head for level 2 and level 1 respectively, you should be good. 129, doing all right. Okay. Oh look, I put words on here. How nice, I forgot I did that. I should have known better. I tend to put words on things. Words are really important. Words are why you make the big money. Yes, Vladimir, would you like to give me some more words? Oh, wait, I can't hear you. Let me make sure if that's my problem or yours. Okay, try again. No, can you all hear him? Okay. Un momento. Unplug it, plug it back in. Okay, try again. Okay, I cannot hear you. Why can't I hear you? Is this thing taking over? No, it's plugged into the right thing too. Okay. All right. Let me change Okay, try again. It's not letting me hear you. I'm gonna try all the devices I can here. Okay, try again. Nope. Damn it. Okay, can you type? I'm sorry. We're making it work. I don't know why. Everything is connected as near as I can tell. All right, the fixed intercept says for a student whose verbal equals 10 at the end. Yes, yes it does. Is your question, is that wrong? But we are using CMC. Okay, so here's why that is okay to say. Because we have centered school mean verbal at 10, and at the student level, they have a score of 0, which means they're at their school's mean. But in terms of this particular reference point, it's a school with 10. So that's an indirect way of saying the student also has to have 10 if they are at the mean of their school, and the conditional school I'm talking about has a mean at 10. Does that make it better? Okay. All right. Thanks for working with me, folks. We only have 10 more minutes of this, but... All right. I honestly don't know. Okay. Anywho. Effect size. That's the next thing here. So in terms of how much variability each of these predictors accounted for, because they've been carved up into their level-specific piles ahead of time, then each one is targeting its own source of variance. So at level 2, we have the between cluster slope of verbal. That has reduced the random intercept variance further. So what it was, remember the formula is what it was minus what it is over what it was. So this is relative to the empty model, so this includes all 3 of our predictors at level 2. Works out to be an R-square for the intercept of 0.53. So I would say that we've explained 53% of the variance in school mean differences, specifically. So it's 53% of the 22% that we had to start with from the empty model. So half of the reasons why some schools have better language outcomes is because of what I have in my level 2 model right now, mixed grade homework and school mean verbal scores. At level 1, we've explained with just this one new predictor, with the within cluster slope of student verbal has explained about 35% of the variance at level 1. So of the about 78% that was within clusters between students from the same school, we've got 35% of that based on just knowing their verbal score on this other measure. You would think that verbal scores predict language outcomes, and you are right. Okay. Questions? Okay, let me back up a slide. I have in the red box here, contextual. Contextual effect is 1.7. Can you look at the numbers and guess where that must have come from? We got one vote for between minus within. That is correct. 3.6 minus 2.4 is 1.2. Now, why do I have this on here? A couple different reasons. For now, I will tell you that the fact that this difference between these two slopes is significant is empirical evidence that we should not smush these things together. 3.6 is significantly more positive than 2.4. The between slope is larger than the within slope. Now, I can't really talk about the effect size for them in the same way, though, because each of these is tied to a different variance component. These are not standardized slopes. If I went with pseudo R-square, I don't think the increase that we got from the between slope was anywhere near the size of the increase we got from the within. The within is actually stronger in terms of effect size. But in terms of unstandardized coefficients, there's a difference of 1.2. Each of these is targeting a different pile of variance, using a different pile of variance in the predictor. They're not on the same scale. But you can still test the difference as your empirical evidence for whether smushing is acceptable. It is not. Okay. Anyone else want to type to me? Thumb sideways still, or have we hit like maybe a 45-degree angle? Not yet. Okay. Somewhere between the two. We'll get there. We'll get there. It's fine. And those of you who were with me in longitudinal last year, like, oh yeah, I've seen this before. Now you get to see it again. Indeed. All right. So recapping then. What cluster mean centering tells us directly is the within slope at level 1. If I have more x than my cluster, do I have more y than my cluster? At level 2, I get the between slope. If I'm from a cluster with high x on average, does my cluster also have high y on average? Cool. Then we get to the third thing, the contextual thing, the 1.2 that I just showed you. That's the third thing people might want to know. And depending on your perspective, in cluster data, it might actually be more useful than the between slope. The contextual slope tells you the difference for between minus within, which is why I could get it out of the previous model, even though I wasn't using a model that directly gave it to me. Or I could change my level 1 predictor and get it out of a different model instead. So the contextual slope tells you what the level 2 effect is after controlling for the level 1 slope. The between effect is not controlling for the level 1 slope, and that's the difference. So if you want the contextual slope instead to be directly given by the model, by the level 2 part of the model, then we can't use cluster mean centering. We have to use constant centering, or what is known as grand mean centering more generally, in which we swap out what's happening at level 2. We have our level 1 original predictor centered at a constant. And I haven't come up with a good way to notate this, so I'll apologize, but I'm keeping the same notation here because honestly, the constant you pick doesn't matter. The constant you pick for centering does not change the information the variable contains, which is the critical part. So you can leave it uncentered, doesn't matter. That's why I'm keeping it the same, because it hasn't changed its meaning. It's only changed where x is, where the 0 is for x. Okay, now here's why you would end up with a different result from swapping out what happens at level 1. We would vote calculus would use a C, so I vote it's fine. Okay, fair, good. Notation is not my strong suit. I've gotten better at it, but I still have a little bit of a ways to go. Question, if we calculate the slopes as within and between effects, but then convert them, the between effects, to contextual, what would be the interpretation of the within effects? They do not change. They will stay exactly the same. And that is the tricky part of all of this. So I will tell you, where we are headed is 2 different versions of the same model. We are going to swap out what happens at level 1 and keep constant what happens at level 2. The end result of this is backwards from what you would expect. The same variable at level 2 is going to change what it means. A different variable at level 1 across models is going to mean the same thing, even though it's a different variable. That's what makes this tricky. Why it changes is because of what you already know with respect to collinearity. So if we go back to regression for one slide here, regular, just single level regression, nothing fancy. You learned that if you have predictors in the model that are not correlated, then each of these slopes carries the full relationship bivariately between the predictor and the outcome. So this would be the case in an experimental design, for instance, if you had a 2x2 design where you randomly assign people to each possible cell such that these 2 dimensions are uncorrelated, then you would have the effect of one dimension be whatever it is, the effect of the other dimension be whatever it is, and because they're unrelated to each other, they don't compete for the same variance. Each one gets its full bivariate effect. But if that's not the case, if these are just regular predictors that weren't manipulated, if these are measured variables in which there's probably some relationship between them, then you get a different story as to what beta 1 is if x1 is in the model with x2 versus if it's all by itself. Same thing for x2. Its effect will change after being controlled for x1 than by itself, because these two are fighting for common variance and neither one of their slopes gets credit for what they have in common. That principle is the exact same reason why the interpretation of things shifts in multi-level models depending on what you have at level 1. So I'll go over this quickly and then we'll stop for this week and pick this up next time. So at level 2, this variable goes in the model either way. So what I have here is illustrating two different clusters and two different people from each cluster. So the first section here has people that get a 2 and a 4, so the average of those two people would be a 3. The second cluster has people with a 6 and an 8, the average of those two would be a 7. So if I'm like, well, 5's in the middle, let's choose that as the centering constant, then level 2x, cluster mean x, is the level 1 mean across the two people from the clusters minus 5. So it's this variable that would go in. So this variable would represent level 2 cluster mean variation in my level 1 predictor either way. The question is, what is it paired with? This is what we've seen so far, the cluster mean column, where we started by building within cluster X as subtracting off the level 1 cluster mean. So then this person gets a minus 1 because relative to 3, they are 1 less than average, and this person is 1 more than average. Down here, even though these people have different values, they have 6 and 8 rather than 2 and 4, relatively speaking, this person is still 1 below their cluster's mean, and this person is 1 above. So this cluster mean within cluster column here, cluster mean centered, only has within information, only relative information. It is not going to be correlated with level 2 because we took it off. The subtraction makes it uncorrelated. In contrast, this column is what you would have if you did grand mean centering. Let's say we pick the same 5. This column still reflects differences between clusters in addition to differences within clusters. We have not changed the information that it contains. That means this level 1 column under grand mean centering is still going to be correlated with this level 2 column. Correlated things fight against each other. So they'll have overlapping variance that neither one of them gets credit for, and that's going to change what they mean when we get them into the same model. So two different versions of what goes in at level 1. The same thing goes in at level 2 regardless of what you pair it with. This is cluster mean centering, which is just variable centering. This is grand mean centering or constant centering more generally. Okay. So I'll leave that there and show you next week the exciting conclusion of what happens when you do grand mean centering instead of cluster mean centering, since it's 144. All right, any other questions or things you want me to repeat quickly before we call it a week? No? All right, then thanks for being here, folks. I hope you all have great weekends. I will see you in person on Tuesday unless I get COVID for a third time. All right. Have a good one. Let me know if you need anything. Good luck with your homework.